This is an important concept known as continuous time convolution in the field of signals and systems. This expression for convolution is given by integral minus infinity to plus infinity x of tau h of t minus tau d tau, that is going to be equal to y of t. And this is symbolically written as y of t is equal to x of t convolution h of t, as has been seen in the previous slides. Convolution, as has been mentioned, is a primary or significant concept in linear system theory, a field similar to signals and systems. The property of convolution is that it helps us to determine the zero state response of any input. As a result, the response of a system at rest, that is at zero initial conditions, is actually the convolution of that input and the system impulse response. Graphical continuous convolution, reflect and shift convolution integral evaluation. Let us go on to see how we would be computing the convolution integral. The convolution integral expression is given by y of t is equal to integral 0 to infinity x of tau h of t minus tau d tau when t is greater than 0 or equal to 0. Major point that needs to be noted is that in both the signals the dummy variable tau has been introduced, which is the independent variable. Now, if both the signals are similar, flip h of t minus tau, which is the normal case, or if both of them are slightly different, flip whichever is easier or smaller to slide. After sliding or moving the signal, find the areas of overlap by evaluating the integral within suitable limits. Flip, shift and multiply. Let us go on to the detailed procedure for this particular. For the detailed procedure, the first step is sketch x of tau and h of t minus tau in terms of the independent variable tau, as has been given in this expression x tau and h of t minus tau. X of tau can be easily sketched, but in order to sketch h of t minus tau, few things needs to be noted. For h of t minus tau, first reflect or flip h minus tau about t equal to 0, giving h of minus tau. This would appear as has been shown here. This has been flipped about t minus tau. Next, only shifting needs to be performed by minus t and start with a large minus t. Shift h of minus tau to extreme left of the discrete time axis t, similar to what has been done in the discrete convolution. So, what needs to be done is this signal, which is lying almost close to t equal to 0, could be shifted to the extreme left of the discrete time axis to show a large time shift minus t. Next, evaluate the mathematical expression for the intermediate signal wt of t. When this signal lies here and the other signal lies here, we could see that the product of the integral x of t and h of t minus tau would be equal to 0. Like this, at each point of t, we need to evaluate the mathematical expression for wt of tau. The next process is more significant in the sense we need to shift, move or slide h of t minus tau to the right till the mathematical expression of wt or tau changes. This is as shown here. The signal has been shifted to the right and we could see that at some point of time t, when t is greater than 0, there is a small overlap, which means there is a small resultant change in the area. This is the interval that we are looking for, and this is the area that needs to be computed, shaded in blue. In each interval of time, shift integrate wt of tau to get y of t for that interval. Identify t at which this change occurs, as this t marks the beginning of a new interval and end of the current interval. And time interval may be written in suitable form. For example, if t is less than or equal to 3, it could be written as in an expression that is suitable to analyze the problem. For the new t, we need to repeat the steps 5 to 7 till all the time shift and the respective mathematical expression are identified, which means we need to evaluate the integral and write the expression for the integral. And again we need to keep on sliding till the entire area of t is complete. And finally, let us formulate the expression for y of t in terms of various t. Let us go on for a simple problem wherein the problem is defined as there are two impulses of area 0 to tau. One of them is called as x of tau. The other one is also called as h of tau. By the principle of continuous graphical convolution, what is done is that we try to flip one of the signals. First step is we try to represent both the signals in the dummy variable x of tau and h of t minus tau, and we flip the signal which is simpler. In this case, since both of them are identical, we have decided to flip the impulse signal. So we have got h of t minus tau, and for any value t less than 0, we can see that there is no overlap between the two signals. Hence, the value of the integration integral given by x of t in x of tau into h of t minus tau over such a period less than 0 would be 0, because there is no overlap between the two signals. And another important thing that we need to consider here is that we have two time instances, namely t minus small t minus capital T and t, which are considered as the limits of the function when we are trying to flip the signal and replace this tau with capital T. So, as has been mentioned, since there is no overlap between the signals, when we shift the impulse signal to the left, we could see that the area of the convolution in this case. Let us go on to consider the second case. The second case we have, if you just see this particular signal, blue color signal, it has been slided little bit, and up to what extent should we slide? We should slide it such that there is a small level of overlap, which means, as has been mentioned, the right end of the signal should be beyond 0. This is the general concept that is followed. So, we are going to consider a region which is going to be defined as 0 lies within t, which is less than or equal to capital T. This is the region that we are analyzing now. So, what happens there? When we consider this region is called as the region of partial overlap, because part of the signal is lying outside, part of the signal is of the impulse signal is now lying within x of tau. Now we need to evaluate this area and fix the limits of integration. The area is this region between 0 to t, as has been given in the integration. So the region is going to be y of t is going to be equal to 0 to t. What would be this particular area? Since it is 1, that is what is the value assumed to be. So it is going to be 1 into d tau, which is going to be equal to t. When we see the signal, we see that this is something like a ramp signal. At t equal to 0, its value will be 0. At t equal to 1, its value will be 1. And at t equal to 2, its value will move on to 2, and so on. So hence we have got between the region of 0 to capital T, the value of the integral is go on to the third case in the graphical convolution by considering the case as a case of complete overlap, as in this particular case what is observed is that the signal h of t minus tau, which is represented by the blue signal with its two time limits t minus tau and t, is going to lie within this particular signal. Since this particular region is a region where there is a lot of overlap, this we call it as the complete overlap region, though a part of the signal lies beyond capital T. So now let us try to go on to evaluate the limits of integration and the area for this specific case. So the case considered here is a case where the signal lies between 0 to t minus capital T is less than capital T, which is what is going to be the region which is going to be under consideration. Can we rewrite this into some small different form? Yes, let us attempt it. Let us try to remove this minus t to this particular region and to this particular region, thereby rewriting it as t is less than, small t is less than or equal to 2t. This is how we have rewritten this particular region. So with this particular rewritten region, let us try to analyze what is going to be the area of the overlap. The area of the overlap is going to be, any guesses? Yes, it is going to be this region, which is again shaded in blue. So it is the region between, as has been given in the limits of integration, t minus capital T and capital T, and since it is a linear expression with same values, the area of the integration is d tau, which is going to be evaluated as t minus small t minus capital T, which is going to result in 2t minus small t. This is going to be the area of the integration in the third case, which is defined by capital T is less than t is less than or equal to 2t. This helps us to consider the third case and why it is mentioned as complete overlap, though some portion of the region is lying beyond the signal. We go on to the last case, which is a region with no overlap, because what happens there is we have shifted the value of the right end of the impulse signal to a condition which is beyond capital T for x of tau. That is what has been mentioned here, and it has been mentioned that t is less than or equal to t minus capital T. This could be rewritten as 2t is less than or equal to t. So during this region we see that there is no overlap, hence by our experience with no overlap region we know that the area of the integration y of t is going to be equal to 0. So we have got y of t is going to be equal to 0. So let us go on to summarize our all results, 4 cases, and let us see how the graph could be drawn. At y of t, at t less than 0, y of t is 0. When t lies between 0 to capital T, y of t is t, so we can see that this would be a ramp. Similarly, for t lying between capital T to 2t, we could see that the area is capital 2t minus t, and for capital 2t less than or equal to t, we could see that the area is 0. Any guesses what could be the value of the signal? Here, already as has been discussed, this would be an increasing ramp and this would be a decreasing ramp, as can be seen in the figure. So we could see that this region between 0 to t, this is an increasing ramp as has been shown here, and from 2t minus t, which is the region between t to 2t, we could see that it is a decreasing ramp. At t equal to 0, our region value would be 2t. At t equal to 1, the value changes, so on, which means that it is going to be a ramp in the negative direction. This is what we have obtained as the solution for the convolution of two impulses x of t and h of t, whose time period was capital T. Let us consider the example where two functions are given defined by f of t and g of t. F of t is a function which lies with a time value of 2 and an amplitude value of 2, and g of t is a signal which lies between a time value of -2 to +2 and amplitude of 3. Let us now try to replace t with tau in f of t and g of t, resulting in f of tau. And let us go on for the second example step by step. The convolution, as can be seen, could be divided into 5 parts. Let us see what are those 5 parts and how we have arrived at those parts. The first part is being considered is t is less than -2. The reason being, when t is less than -2, this region is going to be substituted with a value less than -2, which means -1. So still the value would be 1, which means it has not got an overlap. Since the two functions do not overlap, we could see that the area of the integration is going to be 0. Next region would be, we would like to slide the function little bit and slightly move it such that the value of this function is slightly greater than 0, but it lies between 0 and -2, and as can be seen here, since it has slightly increased beyond 0, the value of the function is going to be something like this, and the area of the integration would be an area which is covered by this region given by a product of 3 into this region, which is defined by -τ plus 2, and the limits of the integration, as can be seen in the previous case, is going to be 0 to this region, which is 2 plus t. So on substituting this region and integrating, we would be getting 3 into -t squared by 2 plus 2τ between the limits 2 plus t and 0. On simplification, this gives us -3t squared by 2 plus 6. Next, we will start with 0 as the starting point for our area of overlap and see how this works. Hence, the area of the time period is going to lie between, t is going to be between 0 and 2. So, under such a case, what we see is that since t is less than 2 but greater than 0, this is how our function looks like, and the area under such a product would be similar to the previous case with a difference in the limits starting from 0 to 2, thereby giving us a value 3 into -τ plus 2 dτ, which is a constant, resulting in 6. Since we have stopped the sliding with t equal to 2, now let us go beyond and see what would happen when t lies between, t is less than 2, t becomes slightly greater than 2, but it is going to be less than 4. During this case also, we would be having an overlap which could be seen and calculated similar to the previous case, and it is easily obtained. When t goes beyond 4, we see that g of t and f of t do not overlap, and hence the area under the product is 0, as is the normal case. Because when t is greater than 4, this becomes plus 4. So this is also going to be beyond 2. A value greater than 4 means we may even put 5. So this becomes 3. So this goes beyond this region. Hence our value is going to be shifted. Hence the solution of the problem with 5 intervals are going to be as shown here. Y of t is the convolution of f of t and g of t given by 0 for t less than or minus 2, minus 3 by 2 t square plus 6 for t between minus 2 and 0, 6 between 0 and 2, and 3t squared minus 12t plus 24 for t lying between 2 and 4, and 0 for t greater than 4, and these regions are defined as no overlap region, partial overlap region, complete overlap region, partial overlap region, and finally the no overlap region. The final solution is going to look like when t is less than minus 2, there is no overlap, which means the value of the signal is 0. Between minus 2 and 0, the signal is having a function similar to an exponential given by 3 by 2 t squared plus 6, and between 0 to 2, it is a constant region given by 6, and from 2 to 4, again we have something like a decreasing exponential. And beyond 4, again the value of the signal is 0. We will go on to one more example considering the evaluation of the convolution. Here the graph considers u of t minus 1, and the second value is e power minus t into u of t. So, deciding to flip the step function, we would be getting it as u of minus tau minus 1, which is shown here on flipping, and on flipping and shifting we would be getting the function like this. So, applying our concept of continuous convolution, we would be obtaining it as, since on shifting we are getting a signal like this, we would be getting that the exponential signal is kept without flipping, which means e power minus tau into u of tau is kept without flipping, and this is having a value t minus 1 to minus 1. So as a result we would get conditions for t minus 1 is less than 0. When that happens, which means t is less than 1, as a result we would get the value as 0, and for regions t minus 1 is greater than 0, the exponential value would be ruled by e power minus tau, and hence we would be getting it as e power minus tau d tau between the limits 0 to t minus 1. So thereby for regions what we have got, the evaluation of the integral results in 0 to t minus 1 e power minus tau d tau, which is going to be 1 minus e power minus t minus 1 when t is greater than 1, and y of t is going to be 0 when t is less than 1, resulting in a solution like this. We would go on for a last example considering a signal which is h of t. So considering such a case, we are going to shift the exponential signal. As a result, when the signal is lying less than 1, we would see that the area of the overlap is 0, because this is what we get on flipping the signal. So when t is less than 1, the value of the signal would be 0, resulting in y of t is going to be equal to 0. On the other hand, when we keep on sliding the signal and bring it into a position such that the signal lies between 1 and 2, as has been given here, our area of integration would be between 1 to t, and our function would be what is the exponential given by e power minus t minus tau dt. And still, if we shift the signal, we would get the signal beyond 2, and as a result our integration value would be e power minus t minus tau d tau between the limits 1 to 2. Thus, our solution would be between 1 to t, the value is 1 minus e power minus t minus 1, and beyond 2 it is going to be e power minus t minus 2 minus e power minus t minus 1. Next we go on to the important properties for convolution. The first property is associativity, which states that x of t into v of t into w of t is going to be equal to x of t into v of t into w of t, which means the order of multiplication is immaterial in this case. The next is the commutative property, which is given by x of t convolution v of t is going to be equal to v of t convolution x of t. The third property is distributivity with respect to addition. Here we could see that it is x of t convolved with v of t plus w of t, which is going to give us x of t